Hi everybody, today I thought we'd have a look at a new project. I'm going to have a look at a function generator. Anybody that's been following my channel will have noticed that in the past I did do a function generator some while back using the XR2206 IC. You'll recall at the time this was the project that we built. Well, it was fairly basic in its operation, and what we're going to do today is still use the same IC, that's the XR2206. But this time we're going to look at improved ways of altering the frequency and doing all the switching for the frequency ranges and the waveform selection as well. So let's first of all have a look at an overview of the project today. Right, well here we see an overview of our project today. It's in three main blocks. We have the main function generator block on one printed circuit board. We have the power supply module on a separate PCB, and we have the display module, which will also have an I2C bus module attached to it because it'll be driven by I2C from Ardunio Nano. So they're the three main building blocks of our project. The main function generator module is going to include the XR2206 ICs we have in the past, and that's going to generate the waveform outputs of either a sine wave, a triangular or a square wave out. We're also going to have a TTL output. We'll clean that up with a Schmidt trigger, so we get a nice clean square wave output of 5 volts peak to peak. There's a TTL output there, and the normal output will have some amplification there with an op amp, of which we can control both the gain and the DC offset. I'm going to try DC offset. I'm just not sure how effective that's going to be. We'll have a go at trying to add some DC offset to our output waveform. In addition to that, this particular function generator IC has the ability to have an amplitude modulated input, so we can put that as an option. So I'm going to include that as an option if you wish. And because of that, I'm going to have another pot there which will set the carrier level for the AM modulation. Now the difference to this function generator to our previous project is that we're going to try and control the IC, the function generator IC, not from a potentiometer in terms of frequency, but from a rotary encoder. So we're going to use a rotary encoder to set the frequency. I'm also going to use the push button on the rotary encoder to select either coarse or fine frequency adjustment. And I'll show you how that's done shortly. We're also going to include some CMOS switching on this module, and that will allow us to switch both the waveform output with a single push button, so we can toggle through the different modes, and we can also change the frequency range again with a single button, toggling through the frequency ranges. So that simplifies the control in terms of both the waveform selection, the frequency range selection, and the frequency itself. So all of that is going to be on one PCB, and that module is going to be driven with a power supply giving us a plus and minus voltage. Now I'm going to give two options here. We can either have plus and minus 9 volts driving the main function generator board, or we can have plus and minus 6 volts, and that will depend on the quality of the XR2206 ICs that you have. Now this particular IC was actually obsolete. In the original manufacturer, EXR, stopped manufacturing this IC way back in 2011, I think. And since then, the ones you buy today on eBay are actually clones of the original IC, so they don't seem to have the same specification in terms of the power supply rating. So because of that, I'm going to give an option on the power supply where we can run it at a lower power supply of plus and minus 6 volts, or the higher one at plus and minus 9 volts, depending on the quality of the IC that you purchase. And I'll show you shortly some of the different ICs that are available on eBay. Here we see an example of some of the function generator ICs I purchased on eBay for this project. They're all very, very similar, apart from the stamping, the markings on top of the IC. The top one there and the bottom one here, you'll see are very similar in their markings, apart from what appears to be a date code. The top one has got a code there of F0918, and the bottom one's got F0919. Now of those two ICs, I found that the top one to be the best, and it's in fact the top one with the date code F0918 that will operate at the higher voltages of plus and minus 9 volts, whereas the bottom one here I found I had difficulty with, and in fact that only seems to operate in the main on plus and minus 6 volt supply. You may get some that will operate at higher voltages, but I found most of them with this marking on does not, and even if it does run quite hot and draws more current. Now the middle one there you'll see is somewhat different in terms of the markings. There's no logo marking on this particular IC, just the stamping of the IC type XR2206CP and the letters HLF. But what I have found is that this particular IC does work very well, and certainly operates at the higher supply voltages of plus and minus 9 volts. Just one final point with regard to the power supply. The positive voltage from the power supply is also driving the Arduino Nano, and then you've got a little 5 volt regulator on the Arduino Nano, and I'm going to utilize the 5 volts coming out from the Nano to not only supply the rest of the 5 volt logic on this board, but also feeding it back to the power supply. So we'll have a little socket on the power supply with 4 pins on it, ground, 5 volts, and then the plus and minus voltage there, and we'll utilize that maybe for future upgrades. Let's now have a quick look at the function generator IC we're using in the project today, the XR2206. And here you see a simplified block diagram of the internal workings of that IC. Internally we have a voltage control oscillator, we have a current switch, and we have a voltage reference source. The timing of the frequency of that oscillator is determined by a timing capacitor connected across pins 5 and 6 of the IC, and a timing resistor, in this situation here, connected between pin 7 and ground. Now the timing resistor can be selected to either use pin 7 or pin 8 by means of this current switch, and the current switch is controlled by the logic level on pin 9 of the IC, which is referred to as the FSK, the frequency shift keying pin. When the logic level of that pin 9 is high, or it's left open circuit, the situation is as we see here. The current is switched through pin 7 through the timing resistor to ground. If the logic level on pin 9 is taken low to 0, then the timing current is switched down through pin 8 through an alternative timing resistor to ground, and in that way we can switch between 2 timing resistors and effectively between 2 frequencies. But at the moment we're going to stick with just using pin 7 for our project today, but we may utilize that feature of switching between the 2 a little later. Now within the IC we have this voltage reference source, and that voltage reference is with relationship to the ground pin, in this case pin 12, and the typical value of that is around 3 volts. And what that's going to do is it's going to fix the voltage on the top of the timing resistor at the voltage reference level, which in this case is going to be 3 volts, and therefore the timing current is going to be a function of that voltage across it and the value of the resistor, and that will give us a timing current for the voltage control oscillator. And then the relationship between the frequency of that oscillator and the value of the timing current is a linear one, and here you see a small graph here showing you that as we increase the timing current, the frequency output also increases equally in a linear fashion, and we get out of this oscillator a nice triangular waveform which is later shaped to either a sine wave or square wave output as required. Now at the moment our circuit here that we've shown is all with respect to ground, so we've got a single supply, so we've got a positive voltage going on pin 4 and pin 12 is going to ground, so the voltage there is always with reference to ground. And what I want to find out now is what that timing current is. What is the range of that timing current? And as it happens, if you look at the datasheet for this IC, the manufacturer gives you a minimum and a maximum recommended resistor for that value, which maintains the stability of the oscillator over its range and over a temperature range. So if you look at the datasheet, you'll find that they recommend that the minimum value for that timing resistor is 4k ohm, and the maximum value should be no higher than around 200k ohm. And with those values we can now work out what the minimum and maximum timing current is allowed through the timing resistor. So if we calculate that out, we know that IR is equal to the voltage divided by the resistance. Now we know that the voltage on the top of the timing resistor is always fixed at 3 volts, so that's a fixed constant voltage. And if we take the value of 4k first of all, that 4k resistor, so we divide it by 4k, and if you do the calculations for that, you'll get a current of 750 microamps. So 750 microamps is our maximum timing current that the datasheet is suggesting that we should use. If we now look at the other extreme with the 200k resistor, so we simply divide the 3 volts now by 200k ohms, and the timing current value you get there will be 15 microamps. So according to the datasheet then, we have a maximum minimum of 750 to 15 microamps current, but what I want to do in our circuit today is not just go to the limits. I want to try and make the oscillator as stable as possible, so I'm going to stay well within those limits. So I'm going to choose the highest current for our design today of 700 microamps, and I'm going to go all the way down, not to 15, but I'm going to take it down to 50 microamps. So in our design today we're going to design the circuit so the timing current flowing through that resistor is going to vary from 700 to 50 microamps. Now normally with these circuits you see that the easy solution to change the timing current is to make that resistor a variable resistor, but we're not going to do that today. What we're going to do is disconnect that resistor from ground, and then we're going to apply a voltage at that end of the resistor to give the correct timing current flowing through it. Now before we can calculate the voltage swing at this end of the resistor, we need to know two things. We need to know what the value of the resistor is, and secondly we need to calculate the voltage drop across it for the current swing. Now if you recall that in the datasheet I mentioned that the manufacturer suggested that the minimum value resistor for that would be around 4k. Well, the nearest standard value to 4k is a 3.9k, so we're going to use a 3.9k resistor for that value today. And knowing that, we can now calculate what the voltage drop is required across that resistor to give us both 700 microamps and 50 microamps, and from that we can then calculate the voltage swing at this side. So in the first instance, VR is going to equal the current multiplied by the resistance. We know the current initially there is 700 microamps, and we know the resistance is fixed at 3.9k, and if we do that calculation there, it'll give us a voltage drop across the resistor of 2.73 volts. So when the current is 700 microamps, VR is equal to 2.73 volts. Let's now do the other extreme at 50. This time we have a current of 50 microamps. The resistance is still the same at 3.9k. And this time when we do the calculation, the voltage is 0.195 of a volt. So now we have the two extremes, so that's going now to 0.195 of a volt. From this information we can now calculate the voltage swing at this side of the resistor, but before we do that, the circuit as we see it here is off a single supply, so we have a plus voltage there on pin 4 and pin 12 is going to ground. But in our circuit today we're going to use a split supply. Initially we're going to use plus and minus 6 volts, so instead of this line going to ground, that's going to be going to a minus 6 volts, and that is going to go to a plus 6 volts. Now once we do that, the voltage reference now, with the voltage reference in the IC, is going to change, because pin 12 is no longer at 0 volts, it's at a minus 6. And remember we said that pin 7 would always be 3 volts higher than the voltage on pin 12. That's the relationship between the two. Since we've now changed pin 12 to a minus 6 volts, the output voltage there will now change to a minus 3 volts. So we now get a negative voltage on pin 7 as opposed to the positive voltage we had previously. Now we need to calculate the voltage swing at this side of the resistor to give us the current swing from 700 to 50 microamps, and we can do that quite easily by looking there and saying that the bottom end swing, we've got minus 3 volts. We need to then take off the voltage drop, which is minus 2.73 of a volt, and that will equal to 5.73 of a volt. But remember, that is a negative voltage, so at this end of the scale we'll need a negative 5.73 volts. Now at the other end of the voltage swing, at that end, we know the voltage drop across the resistor is 0.195, therefore we have our minus 3 volts again, and then we minus the 0.195 of a volt, and that will give us a minus 3.195. So that means the other swing is then that negative voltage, so we now have a voltage swing going from minus 3.195 to a minus 5.73, and that will maintain that voltage drop across the resistor, which will give us the required current flow. Here we now see the circuit arrangement we're going to use in our project today to deliver that negative voltage swing on the other side of the timing resistor. We're using a 12-bit DAC which has 0 to 4095 steps. That particular DAC we're using has got an internal voltage reference source of 2.048 volts, and it's also got a ×2 gain amplifier, so we can double that. So effectively the output of our DAC is going to deliver a voltage swing from 0 to 4.096 volts. That voltage is dependent on the rotary encoder and the information then fed to the input of the DAC. Now remember, we need to generate a negative voltage, so we put it through an inverting amplifier, but we need a higher voltage as well than 4.096, so we need some gain on that, and this inverting amplifier is powered from a plus and minus 6 volt split supply. So we can then set the gain of the amplifier to get exactly at that point minus 5.73 volts when the output from the 12-bit DAC is at maximum of 4.096 volts. Now for the other end, which is the minus 3.195 volts, we simply need to determine the output from the DAC that will achieve that and set that accordingly in the software. Here we now have the full block diagram of our function generator today. Across the middle there you can clearly see the bit I was explaining earlier, where we've got the timing resistor going on pin 7, and there's the 12-bit DAC, which is supplying us with the voltage, which is controlling the voltage on the other end of the time resistor to give us our changing current, our timing current. Remember that the function generator now is using a split supply, so we've got a plus voltage on pin 4, a negative on pin 12, which means we've got a negative voltage then on the pin 7, the reference voltage. That means that the output from the DAC goes through a buffer, an inverting amplifier, to give us a negative voltage there. We have some means of adjusting the amplification of that negative voltage there to set it to the correct level. Pins 5 and 6 is where we put the timing capacitor. We've got 3 options there, C1, 2 and 3, and one of those is selected with this analog switch here, which is controlled from the Arduino Nano and from a range select button there on A3, and it simply just toggles round. So when you press the button once, it selects one option, you press it again, goes to the next, then to the third, and then back to the first again. So it just toggles around those 3. We have a display connected via I2C bus to the LCD. It's a 20 by 4 display. That's run from the 5 volt supply. Remember that we're generating the 5 volt supply from taking it from the Arduino Nano regulator, and we're also going to use that 5 volt supply for the DAC and the other logic circuits. You'll see here on the output there where we've got the amplitude adjustment for the sine and the triangular waveform. We can select one of those by another analog switch there, which is controlled by the AO pin of the Arduino Nano, and we can also select whether we connect the preset resistor across 13 and 14 to give us the shaping for the sine wave. So that switch is closed during sine wave operation and open during triangular wave operation. There is the symmetry preset between 15 and 16, and the slider of that is going now to the negative supply. Now the output from the function generator IC is then coming from pin 2, where we've got either the sine wave or the triangular wave, which is determined by this switching arrangement here. It's then going through a analog switch before going to the output. On pin 11 of the function generator IC, you've got the square wave, sometimes referred to as the sync output. We reduce that in amplitude by a potential divider by about 50%. It now goes to a square wave amplifier where we have some adjustment of its gain, so we can match the gain of the output from that with the gain of the output from the sine and triangular waveforms. So the amplitude of the waveforms is kept the same. That then goes through the output switching, the analog switch there, before going to the output stages here. Also coming from pin 11, we have a Schmitt trigger, which is clamping the voltage of the square wave at 5 volts, and that's going to the TTL output. The output from the switching arrangement here, the output switch is going through a buffer. We can set the gain, goes through an output amplifier where we can put some DC offset there. We'll try and do that, and then we've got the output signal at that point there. So there we are. That's the full block diagram of our project today, and what we'll do now, we'll just have a quick look at the full schematic, and then we'll have a look at the builder project itself. Here we now have the full schematic for our main PCB of our function generator today. I'll just go over an overview and then we'll zoom in and have a look at the different areas of this schematic. There you can see we've got the function generator IC itself, the XR2206, and on the other side here, there we have the Arduino Nano. You should clearly be able to see the logic or the CMOS analog switches there, and the DAC, the digital analog converter, is in that location there. So what I'm going to do is I'm just going to zoom in first of all and have a look at the area where the DAC is. Here is a close-up of the area around the DAC, which is being controlled by the Arduino Nano, and we're using the SPI bus, and in that case we're using D10 for chip select, D11 for the data, and D13 on the Arduino Nano for the clock signal. That's all then driving the DAC. I'm also making provision there with a little socket for the SPI bus for future upgrades, so I've got access to that. The DAC itself we're using is actually a dual 12-bit DAC from Microchip. It's the MCP4822, and it has two outputs there independent of each other. Initially we'll only be using output from VA, which is at pin 8, but at a later date we'll actually be using the other output on pin 6 for some future upgrades to this project. So pin 8, the output of the DAC, comes up here and it goes to an op-amp which is configured as a buffer. So we've got a buffer there which is just ensuring that we're not putting any loading onto the output of the DAC, and then the output of the buffer will then go into an inverting amplifier. You'll also see that pin 6 of the DAC, which we'll use later, is going to a similar buffer and then to an inverting amplifier where we have some gain control, and again then that goes to control the timing resistor, but that's for the upgrade later. So let's first of all follow through the output, which is coming from pin 8 of the DAC through the buffer, goes to a reference point there called CNT. So let's have a look at the other part of the circuit where we take that signal to control the timing resistor. So then the output from the buffer, which is the DAC signal, is now going to this inverting amplifier here, and again we've got some degree of control of that with RV2 to set the maximum voltage swing on the output, which will be a negative voltage. But remember, we wanted something around a minus 5.8 volts in our project today, and that voltage is then fed to the end of the timing resistor. In this case it's R19, and the other end of that resistor is going to pin 7 of the function generator IC. So that's how we achieve our voltage to the other end of the timing resistor. And you can just see there a second timing resistor, R21, which is going to pin 8 of the function generator IC, and that's being controlled by CNT2, which I pointed out earlier. And that timing resistor we're not going to use today, but we will be using it for future upgrade on this project. Now the next thing we'll look at is actually the logic switching on this circuit. Here you can see in the center we've got an IC which has got 4 logic switches in there, 4 analog switches. This is actually Analog Devices ADG452 IC. The reason I chose this particular switching IC is its on resistance is very low at only 5 ohms, and that's exactly what we want when we're switching in our timing capacitors. So you can see here that we've got 3 capacitors, and these are the ones that we will switch across pins 5 and 6 of the function generator IC to choose the frequency range. The top switch there is being used to connect the little preset that sets the shaping for the sine wave output. There's the preset there, so that's setting the shaping when we switch from triangular to sine wave output. Now all of these switches are controlled from the Ardunio Nano, and they're just simply coming from data pins. Now the other switching IC that we're using, I'll just move down to that, is this one here, and you'll be familiar with this because we used this on one of our previous projects. We used this on the DC calibrator project. This is the DG3B. This has got like a switch over in it, so when one switch is on the other is off, and you just toggle them over. And I'm using this to switch between sine wave and triangular waveform in terms of switching the amplitude settings for that. And I'm also using it to switch the output. You'll see there that we can switch the output then from sine wave, it'll be either sine or triangular wave, or square wave to the output amplifiers. The next thing we'll look at here is the output from the function generator IC. Remember, we've got the outputs coming from pins 2 and 11. Pin 2 is where we get the sine wave and triangular wave output, and pin 11 is where we get what they call the sync or the square wave out. So looking at pin 2, the output from pin 2 is then going through a amplifier. This is a non-inverting amplifier in this situation here, where we have some degree of control in the gain of that with, in this case, RV5. And the output from pin 11, which is the square wave, is then divided down by 2 with this two 10k resistors there, and then that's fed to another operational amplifier there, which again we have some degree of control in the gain with RV1. So we can control the gain of the, in this case, the amplitude of the signal from both the sine wave stroke triangular wave output and the square wave output. Those signals are then fed into the CMOS switching, which I showed you earlier, which is the this one here, which is the DG303, and then the output from that is then going to the output amplifier. So let's have a look at that. So here we have the output amplifiers. So the input from the CMOS switch is coming in here, goes through a non-inverting buffer there before feeding the gain control, that's RV4, that'll set the output gain. And then where we've got a little isolating capacitor there feeding the signal then to the output amplifier, again it's configured as a non-inverting amplifier, the gain of which is set this time by these resistor values here, this 10k and this 4.7k. The output impedance of the function generator there is set to 600 ohms by having two 1.2k resistors there in parallel on the output. Now what I'm also trying to do here, and I'm not 100% sure just how efficient this is, but we'll give it a try, is to add some DC offset voltage to the output amplifier so we can shift the level of the signal coming out on a DC voltage. And all I've done here is, instead of taking the resistor, that R15, down to ground, I've taken it to ground through a 1 microfarad. This is not electrolytic, it's a normal 1 microfarad capacitor, so it's non-electrolytic. And then as far as signal is concerned, that point is ground, but we can inject a voltage at that point. And what I'm doing here is I've got a potentiometer, a 10k linear potentiometer, where I've got plus 9 volts or plus 6 volts on one side and minus 9 or minus 6 on the other, so we can swing between the two, and we can apply that offset voltage to that point there, which will then effectively sit this output amplifier on that voltage and hopefully shift the output signal. So we'll give that a go and just see how that works. So that's the output stage, and then finally let's just have a quick look at the TTL output. And you can see here I've got the TTL output there. I've got my Schmitt triggers, I've got a few of them wired in parallel, and you'll notice here I've got a transistor, just an NPN transistor. So we're taking the signal which is coming from the pin 11, it's also tapping off of that divide by 2, those two 10k resistors. I'm feeding it to the base of the transistor, and the output of that is then at 5 volts effectively, because I'm supplying that from a plus 5 volt supply, and we're feeding that 5 volt square wave signal to the Schmitt triggers that then clean it up and make sure we've got a nice square wave output there. And again you'll notice I've got 3 resistors here effectively in parallel. These are 1.8k, and that maintains the output there, the TTL output, at also at 600 ohms. Before I forget, just let me show you the rotary encoder part. There we have the rotary encoder, and the wiring arrangement I've got here is to overcome any bouncing, so debouncing the hardware debouncing, and also on the switch itself I've got some hardware debouncing here on the switch. And remember, it's the switch we're going to use to adjust the between fine and coarse adjustment on the frequency control. On the right hand side here of the schematic you can see we've got some sockets here, some 2-pin sockets, and this is where we'll plug in our push buttons for both the frequency range switching and the waveform selection switch as well. So there we have it. There's the full schematic of our project today. Here we see a double-sided printed circuit board I've designed for this project today. We have all the functioning ICs on this board together with the Arduino Nano. The board itself is 10 centimeters square, it's kept at a standard size. Here is a detailed drawing of the layout of the components on the main PCB, and you'll notice that I've tried to keep all the connecting sockets running along the front there, which go to the front panel. So we've got the gain control, that's the output connector, the DC offset control, the rotary encoder, the display, and these are the push button switches that we'll be using on the front panel. And there we have facility for a future upgrade to get access to the SPI bus. Now, some of the other sockets I've provided, there we have the power supply connection to the board, and I've also got the TTL output there, which we may have that on the reverse of the case, so that's why I've situated that towards the back of the PCB. And also I've got on this side of the board the amplitude modulation input there, and the carrier level for that. Again, I've put them at the back of the PCB because that may be a feature we want to have on the back of the project case. Here we now have the printed circuit board with all the components mounted. I've decided to use sockets for all the ICs and also for the Arduino Nano. It just makes it easier and certainly ensures that when you're soldering all the components onto the board that you're just preventing any damage to the ICs due to the heat of the soldering iron. So there's the board with all the items mounted. Well, the next thing we're going to do now is go through the initial setup of this function generator board, and before we can do that we just need to put a little shorting link in place of the AM carrier potentiometer. So if you look at the edge of the board there, we've got a 3-pin socket which would normally go to the AM carrier level potentiometer, and then there's the socket which is the AM modulation input. So what I'm going to go is from the center pin of the plug there to the pin nearest to the AM input socket. So I'm just going to put a little shorting link in there, little shorting plug. So here we can see the little shorting plug there I've got between the center pin and the pin nearest to the AM input socket. Now, I've put together some provisional software for this project today, which we'll modify as we progress, but I just want to point out two of the global variables relating to the rotary encoder. The encoder maximum value and the encoder minimum value. I've set the maximum to 4095 and the minimum to 0, and that's because we're using a 12-bit DAC. Now remember that when we're setting the voltage swing on the timing resistor, the minimum voltage is not a 0 voltage, it's a minus 3.195 of a volt. So we need to find out what the encoder minimum value is to reflect that value, and we'll do that in setup, and then we'll change that value from 0 to the value that we find in our setup procedure. Now, for the initial setup of this project, I've just got the LCD display and the rotary encoder connected to the main board, and I've got the board powered externally from a plus and minus 6 volt supply via the power socket leads there, and I've got a multimeter connected between ground there at the moment because I'm going to check the voltage on the left hand side of R19 shortly. I'll now power on the PCB, and we'll see the intro screen initially. It'll then go to a simple display where we can read the output from the rotary encoder, which will be going from 0 to 4095. Range 1 is just the frequency range, and the sine wave is just showing us the type of waveform coming out. It's set to sine wave by default. The control feature there, I mentioned, the button on the rotary encoder will allow us to step in increments of 1, increments of 10 or increments of 100 just by pressing the rotary encoder button when we're altering the value, and we'll see that shortly. So the next thing we're going to do is we're going to set up the voltage on the left hand side of R19, so we get our voltage range we require from minus 5.73 to a minus 3.195 of a volt. So the first thing I'm going to do is connect the other end of the meter to the left hand side of R19 on the board with a little crocodile clip. There we now have the meter connected to the left hand side of R19, and we're reading the voltage there. The encoder value is set at 0 at the moment. So what we're going to do is increment that all the way up to its full range of 4095 by using the rotary encoder. I'm just going to press the button on the rotary encoder to get over to times 100, so you can see we go up in steps of 100, so you get there a bit quicker. And it's now set at 4095, and you'll see that the reading on the meter is giving us a minus 4.493. We now have to adjust RV2 to get a reading of minus 5.73, which is what we require. So let me do that. So I've got it there set now at minus 5.73. That's quite close, so I'll leave it there. So the top end of our voltage swing there is set. I should say the bottom end in this case, because it's minus 5.73. And I have to set the minus 3.195, and we do that now by adjusting the rotary encoder until we get down to that value. So let me do that. I'm just going to press the button on the rotary encoder to so we can trim it a bit more finely, one at a time. So we now want to go to minus 3.195. Just about there, I think. So I've now set the rotary encoder, so we have a reading on the meter of minus 3.195, which is the other end of our range. And what we now need to do is make a note of the reading on the display. And you'll see here on the display we've got a reading of 2278, and that's the value that we'll need to program in to the minimum rotary encoder setting on our Arduino software. And that's the next thing I'm going to do. I've now updated the software to reflect the minimum rotary encoder setting of 2278 as we just mentioned. So let me now switch on and you'll see the effect of that. So when we start up and go through the intro screen, the setting, hopefully now that's it, the setting now defaults at startup to 2278 rather than the 0. So it limits the range of the rotary encoder to the range that we require for our voltage swing. And you can see here the voltage reading on the meter at the left hand side of R19 is in fact minus 3.195. The initial setup is now complete, so we'll now go ahead and plug all the other controls and buttons into the main PCB and test its operation on the oscilloscope. Here we now have some of the other controls now plugged in onto the main PCB. So I've got the gain control, the DC offset, there's the rotary encoder again, and I now have the two push buttons, one for waveform selection and one for frequency range selection. We'll now just do a quick test of the initial operation of the unit. So let me just power on the unit itself. It takes just a few seconds at startup to go through the startup sequence, and then you should see a sine wave on the oscilloscope. There we have the sine wave. It defaults at sine wave at switch on. We can switch the different waveforms by the push button, so we can go triangular and we can go to square wave, back to sine wave. We can change the frequency with the rotary encoder, and by pressing the rotary encoder we can increase the speed at which we can change the frequency. We can change the frequency range with the other push button, so it goes to the higher frequency. You just got a little bit of spike on there we need to look at, and a higher frequency again, and then back to the lower frequency setting. So that seems to be working fine. Let me just quickly test the amplitude control. So the initial setup seems to be working okay. There's a few issues we need to sort out, but I think we're just going to leave it there for today. There's still some further work to do on this, but we'll do that in further parts of this particular project. In the meantime, I'll give you some links down below where you can download the initial schematic, the layout and the software, and I'll also provide the Gerber files for the PCB as well. Now in part 2 of the project we'll cover off the power supply and get the two modules working together, and then future parts we then go through the total project as a whole and try and improve the operation of it and maybe add some new features as well. So let's leave it there for today. Thanks for watching. If you found this of interest, please give me the usual thumbs up and subscribe, and I'll see you all again soon next time. Bye for now.